Today I'd like to talk about some of the work on electron transfer, and I'll talk a little bit about the history. Although it was such a splendid history that was given before me, I see I could probably do without several slides, but nevertheless I'll go over some of them. I'd like to talk about electron transfers, say a little bit about transfers of 8 protons or hydride ions, and then say a little bit about a very new subject called on-water reactions. They're not electron transfer reactions, but I think the results in the theory are rather cute, and so if time permits, I'll go into that. But if time doesn't permit, I just won't. Well, this is where it all began. Let's go back to the late 1940s. At that time, there were many radioactive isotopes available, of course, from the Second World War, and chemists used them to trace the course of chemical reactions. And in fact, a number of Nobel Prizes were won for various types of work with isotopes and reactions. And in this particular case, these isotopes were used to study the simplest kind of reaction in all of chemistry. As you know, in most reactions, some chemical bonds are broken, and at the same time, other ones are formed, and you have chemistry. In this particular case, in the simplest kind of it, no bonds are broken or formed, just an electron is transferred. And so in a sense, this type of reaction, of which this ferrous-ferric exchange reaction, isotopic exchange is called, is the simplest type of reaction in all of chemistry. Now, the simplicity was several-fold. One, since no bonds were broken to form, one of the biggest difficulties at the time in trying to interpret reactions in detail was absent, namely the calculation of all of the atoms interacting with each other in a state of breaking bonds, and quantum mechanics or computations weren't all that developed as they are now for calculating those rates. So that was absent. Then secondly, in chemical reactions, there have been many studies in which one systematically varies one of the reactants. For example, if it's a proton transfer, maybe one's varied, say, the acid in the reaction and varying the pK of that acid and seeing how that affects the rate of the reaction. So there are many such examples in the literature of how changing the structure by changing the free energy change of reaction, the standard free energy, how that affects the reaction rate. There are many conferences that used to be held on that sort of thing. Well, that's absent here. The so-called standard, the products are, except for where the isotope is, the products are identical with reactants. And so essentially all of these reactions are done with zero standard free energy reaction, essentially. So that means that one of the most important factors affecting the rate is absent here. That permitted people to focus on what's left. So it's because, in the sense of the simplicity of these reactions, that it's possible to go into theory in much more detail than one normally could and obtain some results. So this is a reaction. So here's a reaction where you have a transfer of an electron. Well, the ions are moving around a solution. Occasionally they come near each other, and when they're near each other, there's a certain probability that an electron would be transferred. When they are near each other, when the electron is transferred, you see you formed a ferric ion there and a ferrous. So now this star, which indicates an isotope, radioactive isotope, is now present in the other valence state, and by separating these two ions by precipitation of probably the more highly charged ion, You could then analyze the precipitate for its radioactivity, see how it changed with time, and get the reaction rate. So there are many such reactions studied, and actually also studied in other ways. During those studies, it was learned that there were some generalizations. As you know, in chemistry, in any science, in any field, you look for generalizations where you can. And the generalization was that the smaller ions reacted more slowly. And the question was, how do you explain that? The smaller ions more slowly. This wasn't a matter just of geometrical size. These were orders of magnitude, not just factors of 2 or 3. So how do you explain that? And Libby argued as follows. This was the article that I saw that was in that 1952 symposium. Libby said that, this is quite right, said that when the electron jumps, all of a sudden, well, first of all, the nuclei, the atoms around there, can't move as quickly as the electron. The electron jumps, and for the moment, the atoms are frozen in position, the so-called Frank-Condon principle. So the water molecules around there, around the ion, have a configuration that is not appropriate to the ferric, but is appropriate to the ferrous from whence they came, and similarly for the other one. So during the course of the electron jump, the products were suddenly formed at a high energy state, and that's a barrier. And since the ions interact more strongly, the smaller the ions are, the force fields are much bigger, the electric fields are much bigger. This effect is bigger the smaller the ions, this sort of imbalance of energy, this energy creation and so on. And so Libby argued that explains why some reactions are fast and slow, and how that depends on the size of the ions. Well, I saw that when I was in the library, as mentioned, and I was very excited because the principle that was being applied was a principle that had been devised in the 1920s, the so-called Frank-Condon principle, and it was devised not for chemical reactions, but for other electronic transitions, namely absorption of light, and to relate the absorption spectrum to the structure, bond length, distances, what have you. So that was exciting. But then as I looked at the paper more, I became a little uneasy because something didn't seem right. And as you know, perhaps from your own experience, often you sort of go by some sort of intuition, some sort of feeling. Some things seem right and other things don't. And something didn't seem right. And then I realized that what was wrong was that the postulate of Libby, which seemed so right in applying the Frank-Condon principle, was wrong in this case because it violated the law of conservation of energy. Yes, after the electron jump, the energy of the system would be much higher than before, but where did the energy come from? These were reactions in the dark. These were photochemical reactions that were being studied. And so then the key question was, how do you explain it? I mean, part of it's right, and the other part is wrong. And it became clear that really what had to happen in order not to violate the law of conservation and still apply the Frank-Condon principle was something had to happen before the electron jump and something had to happen afterwards. And I've tried to indicate, that's this one here. I've tried to indicate it on this slide here. This, say, is the two reactants in this case. These triangles are a local artist's representation of water molecules, and they're more highly ordered around the +3 ion than they are around the +2 ion. Also, the bond length, the iron-oxygen bond length, you have water molecules in the first coordination shell, is shorter in the ferric ion. This is exaggerated. The difference is 0.14 angstroms, but nevertheless, it's a significant difference. So this is the configuration before the electron transfer. Eventually, after the electron transfer, you have to have this very different configuration. But when the electron jumps, you can't just change the configuration like that. So you need fluctuations around each of these things, so it's more of a compromise. And then if you do that, and if the energies match, which they do at this point, then you can have electron transfer. So in other words, for the electron transfer to occur and for Libby's basic idea to work, you had to have changes going on in the surrounding solvent, the orientations of the water molecules, in the bond lengths within the coordination shells of each of the ions. There had to be changes which preceded that. Now, when you consider that there are thousands of coordinates, there are these various bond lengths, there are all of these orientations and so on. So there are a huge number of coordinates. So, and you had to take into account changes that were happening to all of them. Frequently in chemical reactions, maybe one focuses on a couple of coordinates, a bond that's broken and a bond that's being formed. But here there were a huge number. So one had to treat, so to speak, that sort of situation ensemble. And one had to find a way of calculating the fluctuations to reach that. Now, at first, this looks exceptional, everything, symmetric, but actually it doesn't have to be all that symmetric. If you consider the huge number of coordinates, let's say thousands of coordinates that are involved around, that play an important role, then on a thousandth minus one surface in this space, you can make the energies of the two states equal, actually. It's, yeah. So there's this huge subspace where this, it's not as beautifully symmetric as that. Nevertheless, the energies of these two basic charge distributions are equal in that huge space. Then there's a question of calculating the fluctuations. How does one calculate the fluctuations, which I just described in more molecular terms? How does one calculate the fluctuations to reach this configuration? And at first, in the first paper, I made use of what's called dielectric continuum theory, where you treat the solvent as a continuum that has a polarization at every place in the medium. In fact, there are various contributions to the polarization, electronic, nuclear, and so on. And in order to reach this unusual state, we needed something which was not the standard electrostatic expression, but one where the polarization was sort of arbitrary every place. So you calculate, so in some way, you calculate the energy of that, or really the free energy of that. And so I found a way of doing that. In thermodynamics, you find a reversible path for producing this unusual non-equilibrium state. So I found that. But it turned out there are an infinite number of possibilities of polarization everywhere that would satisfy the condition that the free energy would be equal of these two electronic structures. And so what I did was minimize the free energy subject to that constraint. The free energy, and anyways, the expression then came out. You know, it's interesting how theories develop. I've seen this several times. I've seen it in nuclear reactions. Sometimes in deriving something, you come up with a complicated expression. If it's a very complicated expression, the chances that the experimentalists are going to be interested in using it is smaller. In fact, maybe very small. And in this particular case, if one looks at the original paper, or 1956, you'll see there's a complicated expression there. But then by playing around a little bit, adding a term, subtracting an equal term, making use of some theorem well known in electrostatics, divergence theorem, we were able to, all of a sudden, and this was a surprise, all of a sudden, a simple expression emerged. Complete surprise. And I've often been asked, did you have a eureka moment? And actually, that was it. I mean, here, I've been working. That was that month. I mean, you might not think it's all that much time, but it was a lot of hours spent there. And complicated things. And all of a sudden, with a little bit of playing around, a simple thing emerges. And that's the expression that's used today. So that's the essence of the theory in its development. Later on, this was a dielectric continuum approach. Later on, I thought that I really should give a molecular approach, a statistical mechanical approach. And to do that, one needed a way of treating a system with thousands of important coordinates, and one couldn't use the usual bond-breaking, bond-forming coordinates that you see that make up the reaction coordinates in many reactions, because there are so many participating molecules involved. And I realized that by introducing an unusual coordinate, I could nevertheless follow the progress of the reaction in that way. And the coordinate was essentially, if you think of this as being a potential energy surface in thousands of dimensional space, and this as being another potential energy surface. Imagine that. And this is sort of profile. Then the vertical distance of these two, which is large and positive, then becomes zero, then large and negative. I use that vertical distance as the so-called reaction coordinate. And you can see how you could progressively, with that coordinate, go from reactants to products. For any one value of this difference, if there are n dimensions, n coordinates in the whole system, then there's a subspace of n minus 1 coordinates that all contribute to the free energy at that particular value of the reaction coordinate. So it's possible to obtain a formulation that had a reaction coordinate that was sufficiently general. There's also another thing. It's interesting how sometimes systems are inherently perhaps complicated, but in one way or another, something may come up that simplifies them. In this case, the individual motions of the molecules in the solvent are quite anharmonic. So everything's pretty complicated. On the other hand, when you're dealing with a large collection of coordinates, there may be a kind of simplicity. For example, it's known in some systems that the response of the system, the polarization to a change in electric field, is proportional to the electric field. Correspondingly, the free energy of the system goes as a square, as a parabola. Even though the actual individual motions of the many coordinates that go into making that free energy are very anharmonic. And this was then later confirmed in computer simulations. So, even though the molecular potential energy surface in many dimensions is complicated, this ensemble of free energy calculated versus reaction coordinate is relatively simple. And that meant that one would end up with a simple expression for the rate of the reaction. I won't try to define each of these things, but they're related to the various molecular properties. So this was the expression that emerged, and as I say, it emerged surprisingly because if you look at the papers, the intermediate expressions were complicated. It was then, this expression, we applied it to quite a few different things, made 5 or so predictions for different things, and by and large those predictions were confirmed. The predictions were of the nature of what is the effect of the driving force, so to speak. Here it's the standard free energy reaction. In an electrochemical case, if you transfer an electron from an ion to an electrode, it's the electrode potential minus the standard potential. What's the effect of that on the reaction rate? Also, if you can look at these isotopic exchange reactions, instead of considering them, if you consider what's called cross reactions between two different kinds of things, it was possible to make a prediction on the rate of that reaction in terms of isotopic exchange and an equilibrium constant. And similarly, there's prediction on an electrochemical reaction rate and so on. So there are a number of predictions, and here is an example of one of them. One of the aims of electrochemists for quite a long time was to, they measured the rate of the electron transfer at the electrode as a function of the metal solution potential difference. And the usual expression that was used was that this rate or this current depended exponentially on that potential difference, so-called Tafel plot, Tafel slope. But in the theory, what was predicted was not a linear relation, only for over a short period was a linear relation, but that eventually the whole relation would be quadratic. And so electrochemists, a number of them, tried to extend their variation of the electrode potential to see if they could see that curvature. And by and large, those efforts were unsuccessful. They were unsuccessful because when they changed the potential too much, the reaction became so fast that the slow step was diffusion of the reactants to the electrode rather than the electron transfer itself. But then around 1990, these monolayers of thioalkanes became available, and they were bound to typically gold electrodes, and they could take an electrochemically active ion, for example, a ferrocene ion, and they could study the electron transfer rate for such a system. And the beauty of such a system, there's no diffusion. So the problem with the ordinary studies was absent here. And then, sure enough, experiments were done by Chitsey, and there's the curvature that was predicted. So this is one of the many examples of experimental confirmation. There's another aspect, too, that was very unusual. If you have, remember, for the products, we had something like that. Now, if you look at a whole series of reactants, you can systematically go from that to where they intersect lower, where they intersect near the bottom, and if you continue it, all of a sudden the intersection point starts increasing. Before, the height of it was decreasing, then there's a minimum, and then it starts increasing grain. Now that minimum has been observed because there's some reactions you can study at 4 degrees Kelvin, some electron transfers, and clearly there's no activation barrier there. But this effect of going through a maximum of rate and then slowing down again, something I wrote about in 1960, and this is the so-called inverted effect. And then for many years, people tried to see if they could find it, because it was, in a sense, a counterintuitive prediction. This was a consequence of it. So here is an example where for the ordinary products, the intersection is way up there, but not infrequently, the products may have an electronically excited state. And so instead, because of the inverted effect, you can form electronically excited states. And indeed, in 1967, Al Bard, a famous electrochemist, had some examples of just that. Very downhill reactions that formed instead these excited states. But the direct observation of that turnover took a number of years, and when you do some work, some theory or something like that, there are some things you feel pretty confident about, and other things you wouldn't stake your life on it. It's a guess, maybe right, maybe wrong. It's the best you could do at the time, but if it turns out to be wrong, well, that's too bad. Something's been learned. But in this case, even though for about 25 years people tried to look for a direct experimental confirmation, and the results were negative except for this indirect effect of Al Bard. And so often I've been asked since, well, how did you feel during those 25 years? did you question things? I said, no, I felt sure, some things you feel sure about, and I did then. Anyways, eventually, a combination of an organic chemist, the late Gerhard Kloss, and John Miller, a physical chemist, and Lydia Calcaterra, the student who did the work, did a study where they kept the two reactants separated by some rigid framework so that other processes that would bypass the whole thing couldn't occur. And they got the turnover. And since that time, there have been many, many examples of this effect. Now, the effect turned out to be significant, not just in itself, not just in its novelty, but it was cited by the Nobel Committee as one of the factors, I'll go into that a little bit, on making solar energy conversion efficient. Because if it weren't for this, when an electron is excited, goes over a little bit, it would tend to come back to where it started from, but at a low energy, it's such a strong driving force, but the inverted effect cuts that on, prevents that, and it goes on instead. This is an example of the photosynthetic system. It was given to me by, oh goodness, wrong slide. It was given to me by Mikkel Barley, who drew it. And the idea is something like this in photosynthesis, as perhaps many of you know. The light is collected by various chlorophyll-type molecules. This is a bacterial chlorophyll system. By various chlorophyll-type molecules, and then is funneled by energy transfer into a special pair of those chlorophyll-like molecules. So you have an excited state there. Then, from that excited state, by a series of jumps, electron is transferred across the membrane. Things happen here. Quinones are transferred, are converted. Anyways, the quinones come out, they can be transported, and protons are changed, and you can drive reactions, and so on. So the nature of solar energy conversion involves electron transfer in a key way, and a key thing is, a key aspect, is that once the electron is there and transfers to the next step, it doesn't go back, even though going back would be very downhill and favorable. But the inverted effect is certainly a key factor that prevents it from going back, and so you can harness solar. Anyways, the Nobel Committee cited that in the work. It is mentioned that the electron transfer theory had applications to many different areas, and this is intended to illustrate that it started here, and it's interesting. It starts, the modern era, starts in a tiny corner of chemistry. Isotopic exchange reactions, it's hard to imagine a tinier corner of chemistry than that. But because of their simplicity, it was possible to look into a mechanism in more detail, get some ideas, and then extend the ideas to more complicated electron transfer reactions, and then eventually extend the ideas to proton transfers, where there's some analogy. And this is intended to indicate many different areas which sort of grew out of this. I can't even read it from here, so I don't expect that you will or will even try to read it from where you are. Let's fast forward to proton transfers or hydrogen atom transfers or hydride transfers, which are a frequent reaction in chemistry. Now, some of the same ideas apply, but not as rigorously. You still have this effect that you're transferring a light particle, which is light compared with the heavy nuclei around. So there's some tendency for the nuclei to stay more or less fixed during the actual transfer, which is really the case in the electron transfer, and it was somewhat more weakly so in the H transfer. Under some conditions, that analogy carries over. Namely, supposing that one draws some potential energy surfaces for a typical H transfer process. And what I've drawn here are such surfaces. Here's the transfer in H from a donor to an acceptor. And if one looks at the chemical kinetics books and one sees that, oh yes, several masses are involved, but if one wants to interpret everything in terms of the motion of some reduced mass, then you introduce some sort of skewed coordinate system where these are coordinates of the reactants, and this is coordinate reactants, these are the coordinates of the product, and there's a certain angle which depends on the various masses. So this is in, as you probably know, in all of the chemical kinetics books and so on. And in the case of a proton transfer or hydride transfer, this would involve essentially going from the reactants to the products. These are potential energy contours, so the reactants in here, products there. And under some conditions, the H just tunnels from one region to the other. In other cases, it goes through a conventional transition state. It's a saddle point there. When it just tunnels like that, you have some changes going on in the surrounding nuclei, and it jumps like an electron, and then you get more changes going on. So under those conditions, there's some analogy, not rigorous, but it's a basis for theoretical treatments which use it as a starting point. There's some analogy to electron transfer reactions. Let me go back. Some of the ideas then that were applied to electron transfer reactions have been applied to proton transfer, hydride transfer, and so on. I thought I'd give an example of such a transfer in a particular enzyme. This is an enzyme which normally operates at a high temperature, the thermophilic enzyme. And under those cases, in that sort of situation, when you look at the rate of an H transfer compared with a D transfer, deuterium transfer, you find the log of the rate versus 1 over T, you find parallel lines for the two. In the case of a number of other enzymes, I think I had a list of maybe 8 or 9 of them, a number of other enzymes, you see the same sort of thing. The same slope for the H transfer and the D transfer. And that tells us something. Because if you start using mutants of some of these things, all of a sudden they don't have the same slope. And the question is, what is the significance of having the same slope and not having the same slope? If you think about the mechanism, or a mechanism for this H transfer, it might run something like this. Perhaps in the enzyme, nature sort of has everything prepared. When you're working under the normal conditions, everything sort of is prepared. And that means perhaps that the H before it transfers doesn't have to stretch to get closer to the other atom. Everything's been prepared. If it doesn't have to stretch, it means it hasn't changed its bond frequency, bending frequency, stretching frequency. It means its zero-point energy does not change during the reaction. So if it typically starts off from its lowest state, and the activation consists of the reorientation of various things surrounding this local transfer site, then as a function of temperature, you're always operating from the lowest state of this H, and you have not distorted the frequency of that by bringing things together, so there's no change in zero-point energy of the H before the transfer. If there were a change in zero-point energy of the H, there would be a change in zero-point energy of the D. The difference of the two, there would be a difference of the two, and you'd actually have an activation energy. But if everything remains in the same state, essentially, and no stretching, that just reorganization of the medium, then you'll get this kind of observed behavior. So I assume that's what's happening. There have been some, of course, computations, and I spoke with one of the people who's done a lot of computations, and his feeling was, now of course remember, computations are great, but they're only as good as the potential energy surface you work with. And his feeling was that it was accidental. But I don't think it's really that way. But that's just a feeling I have, and we'll see. Anyways, it's things like this that I think give some sort of physical insight. The particular enzyme that I've shown here happens to be a thermophilic enzyme, but the same behavior is found for ordinary enzymes. It normally operates at high temperature, that's low 1 over T, so it normally operates in that region. If you try to make it operate in a region where it's not suited to, then you notice different slopes. Now you have an activation. It's not operating under the normal conditions. Other things happen to happen. There are also little side issues, too. In this region up here, a reaction is characterized often by the Arrhenius expression, pre-exponential factor activation energy. And in certain classes of reaction, one has an idea of the ballpark of the pre-exponential factor in the Arrhenius expression, roughly its order of magnitude. And what's found for these various enzymes that I mentioned is that it's normal. It's of the order of 10 to the 12th for H's, 10 to 12, 10 to, around that. So that's sort of normal. It's what you would expect for something like this. On the other hand, once you get into the abnormal region, you get huge pre-exponential factors. So you have to modify the theory, and this is still in the state of flux, trying to understand what's happening there. One of the problems is that you have to use a statistical theory to treat these things. If you say try to use computers with molecular dynamics, you don't reach anywhere near the timescales that are involved in these processes. So, and the statistical theories still need to be improved to adequately treat this abnormal region. Anyways, it's sort of one of the open questions of the problem. But the main thing is this, that in the normal region where it operates, you have the same slopes, and that's true for a number of other enzymes that don't show this thermophilic phenomenon. They're ordinary enzymes. I'd like to conclude with saying a little bit about these on-model reactions, because it's another example of a puzzle that I'll try to explain. This is some work of Barry Sharpless, who won the Nobel Prize before this, actually, but for a different type of work. And he and his co-workers found that if he took two organic reactants, dependent on the reactants, if we took two organic reactants and mixed them together to sort of bond each other, form a cyclo addition reaction, the reaction took, the apparatus is very simple. The reaction took 48 hours. This is the reaction, by the way, cyclo addition. Took 48 hours. If, on the other hand, he shook it up with excess water to create an emulsion, it took 10 minutes. And he wondered about an explanation for that, and he sat on the data for a year, didn't have an explanation, and published it. And then one of the students, in fact, I believe it was a student from India, called it to my attention, and I remembered some work that had been done by a totally different technique by Ron Shen at Berkeley, a surface-sensitive technique that looked at the equivalent of emulsions. He looked at water-air and water-oil interfaces. And he noticed that in the kind of spectroscopic method that he was using, so-called some frequency generation spectroscopy, where you have two lasers, one that operates in the Raman and the other operates in the infrared, that because it's a combination of two lasers, that if you applied that to the body of the fluid, you would get no signal. It was centrosymmetric. But if you applied it to the surface, you get a signal. So it's a surface-sensitive method. Using that method, he found that of the water molecules, in looking at the OHs, 25% of the OHs were not hydrogen bonded to the other. In fact, if you look at the structure of ice, there are things sticking up, some of the OHs sticking up. You can't geometrically bind. There's no way you can bind all of them. So we reasoned as follows, that you had free OHs there, which you don't normally have in solution, but you had free OHs there. If they selectively bound to the transition state more than they did to the reactants, you would have catalysis. So that was the basis, and then a student from, former student, a postdoc came down from Berkeley and did some electronic structure calculations, clustered and so on, and indeed found the kind of catalysis. This just tells you a little bit about the results. Here's the different solvents and so on, and here's the one that where the on-water thing, which took 10 minutes, but other things, in solution. Ron Bessel was an early student of this in solution. It took much longer. So the explanation then that we had was that the free OHs, dangly OHs at the surface, catalyzed thing. There's the ice thing. You see them sticking up, little soldiers. And this is the peak here. This particular peak, this is the OH vibration for water. And at this particular peak are the dangling OHs, and this is the hydrogen bonded structure of all the rest of it, and so on, at the surface. So we made use of that in order to apply to the theory. This is a simulation of the surface. Water molecules, the surface, of course, at least in the simulation, very uneven. Anyways, that's a simulation. And this was a result of some calculations. This represents the sort of the mechanism that we're trying to. You have two reactants, and the transition state is more hydrogen bonded than the reactants. One of the reactants, by the way, was nonpolar, so it's essentially not. And so, anyways, this was an explanation, and we made some calculations, approximations. But I think it's an example of how an experimental result can provide unusual things, unexpected things, and be the basis of interesting type of theory developed. I mentioned that I think that in the electron transfer reaction theory, that the intermediate expression looked very complicated. By adding and subtracting terms and using some theorem, it became simple. Big surprise. The same thing happened in a much smaller way in our Arcane Theory. If one looks at the first paper, which was one that Oscar and I wrote together, it looks very complicated. But then I went out to Brooklyn Poly and started to write some other papers. And then I realized all I had to do, we were summing over states and integrating this and that. All I had to do was just interchange summation and integration, and all of a sudden the R came, especially the one used today, came out. So it's an example of where sometimes you get, both these examples, sometimes you get simplifications that just by playing around with things. By the way, Oscar was really a very wonderful and unusual person. He had been ill, and so then I taught some of his courses and did some additional work and so on. Anyways, I went up to Brooklyn Poly. We wrote one paper together while I was still at Carolina. And then I started to, expand and apply the theory to various things. And so I wrote 4 papers. All submitted about the same time to J. Kim Phys. I put his name on all 4 of them. Sent it to him, and he took his name off all 4. I didn't feel good about that, because I thought, he thinks they're not good enough. But of course, they were the heart of our Arcane Theory. So it's an example of the generosity of a person who's a wonderful human being, and certainly a model for many of us to emulate. Well, thank you very much for this opportunity to talk about the work.